So first we start off with solar nebula theory.
Yeah.
Exactly. Okay, solar nebula theory. We start with what? What does solar nebula theory start with?
A nebula.
Thank you.
Oh, that we already talked about.
Okay, let's hear it. What is this?
A nebula.
Stellar nebula.
Nebula.
I was so close. I was like 6 off.
Okay, we start out with the nebula. Now, depending on the amount of stuff in the nebula, and how much stuff gets starting to contract at the same time, will determine how large the star becomes. Okay, this is the massive star, and this is the average star. Okay? Now, I do like how your chart has it better. What color is the massive star? Blue. Blue. Okay. The bigger a star is when it's in its normal life, the more hot it will become. The hotter it becomes, Muscatel, what happens to the color?
It turns red.
The hotter it becomes? Okay, you guys have all handled a lighter. What happens when you flick a bit? Okay. What's the color of the flame at the very bottom?
Blue.
It's blue. It's blue. So make me get out a lighter and show you. Okay. And the top of the flame, away from the heat source, is orangey red.
You know, they
like
water bottles.
You never know what good a lighter can do.
Anything where
Okay, so if you have a lighter, which you should not have, by the way. Okay, look up here. What do you see? What's the color at the base of the flame?
Blue.
That's the color that's the closest to the heat. That's going to be where it's... I'm not flicking my big for no reason over here.
Wait, I can't see it.
Okay.
Oh!
Right here is where it's hottest, where it's blue. And the further away you get from the flame, the color gets much more yellow. Okay? This is cooler flame than it is here.
Why is it so tall?
You guys are not allowed to have lighters. I'm using this as a scientific tool to show you that hot flames are what color?
Blue.
So stars that are hotter, they're bigger, are what color?
Blue.
Blue. Okay? You guys get the point of this demo? First thing we've got is this stellar cloud. It goes into an average star to a massive star. Now, what we're going to do is we're going to write down in our notes. And I'm going to just base it off of this, and you're going to have to write down stuff in your notes. The notes give it to you detail by detail by detail. Blah. What a boring way of doing things. Okay, first things first. Main sequence. Okay, this stage right here, I suggest you draw this in your notes. Or take a picture of the correct order on your sheet.
Wait.
What we have here, we start with the stellar nebula. Now this is that whole concept of solar nebula theory. Our star's created. There you go in a big gas cloud that starts to condense and gets smaller and smaller and starts to spin. You get the protostars. Boom. Okay. Now, I'm going to talk right now about this section right here. This first section. So let me draw like a circle here. So this first section, this is called the main sequence. Okay, main sequence. You have average stars, you have massive stars. So this would be the average. This is massive. Our sun is right here. Our sun is average. So this is our sun.
Oh,
Okay. You will. Okay. Concept. Concept, very, 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 very important concept. Donnell. Sorry, candid camera.
Huh?
We're recording this class, guys, so watch the behavior. Okay.
Oh.
David, what happened?
Okay.
What? No, please.
Hush. Move
I
on.
knew you were going to do that.
Move on. Okay.
Yeah,
This is the main sequence, okay? Main sequence will become very important later. Need to stop. Okay, main sequence becomes very important later, okay? As far as that term. For right now, know that it's in its main sequence stage. Okay, what is important to know is that the larger a star is, the faster the star will die. The larger a star is, the faster it will die. The smaller a star, the longer it will live. Write that down in your notes. Okay? The more massive a star is, okay, the more massive it is going to change the way it lives and dies, and also how long it will live, and how long. Yes, I'll get up there. I'm sorry.
The bigger, the faster it dies.
Okay. If a star is
The bigger the star, the longer it dies.
the bigger a star, the faster it'll die. Think of it like, I hate to say it, but I have dogs. Okay, well I don't hate to say it. I have dogs. Okay, the bigger a dog is, the shorter it will live. So Great Danes typically live 6 to 8 years and they die. It's very depressing to have a dog that big because you start loving on it and before you know it, it dies. But if you have something like a Chihuahua or a Pekingese or these smaller breeds, tend to live much longer. Okay, same thing with stars. Now, if you have a star that's 3 times more massive than our sun, it will go this direction. Okay? If it's 3 times more massive than our sun, so 3 times the size of our sun, it will go the large star direction. Does that make sense? Average stars have this life cycle. Massive stars have this life cycle. There's also a category for small stars, but I'm not really going to get into small stars in this lesson. Okay? Small stars are really boring. They just go small star to white dwarf. They don't do anything else. They're very boring. Okay? We're going to talk about the cool stuff. Okay. When it runs out of hydrogen. It has about 4 billion years left before it runs out of hydrogen. Okay, so for an example, a massive star could live maybe 14 million years or so. A star the size of our sun has a lifespan of 8 billion years. You see the difference there? 14 million to 8 billion. Big difference. These big suckers, they live, they die. They're very quick in the scale of eternity, so to speak. Right, from when time begins to when time ends. If there is a beginning or an ending, we don't know. We're just kind of watching to see what's happening. Enough of that. Okay, but in the scale of what we can see and how long that we have seen as far as time goes, these things live and die very quickly. I mean, the Earth is 4.6 billion years old. Okay, if you look back in the geologic record, 14 million years? That's nothing. It's nothing. You're talking billions of years, now you're talking about something that actually goes a long time.
So if we had a super mass, like start with the sun from the bottom, we would probably be dead by now because they're so old.
Oh yeah, yeah. Yeah, absolutely. Okay, these things put out so much energy. So much energy. In fact, they put out so much energy that if we were where the Earth is now compared to a massive sun, we wouldn't be in the Goldilocks zone, we'd be fried. We'd have to be much further away to survive the amount of energy. Besides the fact that the ones that put out more energy put out more hazardous radiation than our sun does. Our sun puts out primarily Roy G. Biv light. Okay, that's what most of what the sun puts out. It puts out other stuff, but what it primarily is thrown out is that Roy G. Biv light. A massive star could be primarily throwing out X-rays, or not as much, but they could. A lot more of those, and that'd be a lot more damaging to us. Okay. Large star, average star. Okay? we have seen supernovas in the sky. This is a picture of the Crab Nebula, which was observed in the 1800s by astronomers with very primitive telescopes. Okay, so yes, we have seen these in the sky. Okay, all right. So do you guys have what you need for our main sequence? Okay, stars spend 90% of their life in the main sequence. What fuel are they fusing in the main sequence? Hydrogen. They're fueling hydrogen.
Are we gonna have to know the life expectancy or?
I'm not going to ask you how long will this star live, because I don't know. I mean, I can't say this star will live this amount of years, this star will live that amount of years, but you should know conceptually that these stars live much longer than these stars. These stars have so much energy being expended that just it flies through their life cycle very quickly, very, very quickly. All right. Okay, that's what I have for main sequence. Do you guys have this written down?
Yeah.
You have it written down?
You don't.
Okay, now I'm going to move on a little bit. So now we're going to talk about. All right, here we go. This is why I want you to write it down, because I want to erase it. So I can move on.
Lord,
Yes, Sean.
is all this gonna be on Fusion, right?
All of these notes are on Fusion. Yes.
No, what you're saying on the camera.
Yeah, I put the video lectures on Fusion if you haven't checked them out. They're on the left, right-hand
What
column.
you're doing right now is gonna be on.
Yeah.
Yes.
Yep.
Whoa.
Every lecture I've done so far is up on Fusion, except for like the first two before I decided to do the lectures. Okay, now we're in the giant phase. Okay, so now we come to the giant phase. This, boring. What's going on here?
No.
Nothing. They're stable. They're, gravity isn't winning. Fusion isn't winning. They're stable. They're stable. They're stable. This is where they get excited. Okay, you're like, you're crazy, Mr. Gordon. I know. Okay, here, the supergiants and the red giants. Why is this a supergiant and this only a giant?
It's like,
It's just bigger. What makes this one get so bigger?
Energy.
Sorry.
Energy.
Think about the track it's on.
it's burning.
The energy.
No, it's simple. It's in the massive star category. So the massive star is just going to get bigger when we go to this phase. So the red giant, not as big. But it still goes to the red giant phase. Okay? So what goes on in the red giant phase? Why are we a giant? Or I should say, if we're that star, why would we have turned into a star? The giant. What happened? Something had to happen to cause instability in the star for the star to swell like a big fat tick. Okay? It ran out of hydrogen, or it's running out of hydrogen. Okay? Alright, runs out of hydrogen. Okay. What did I say will always win in the end? Gravity. Maria, what always wins in the end? Gravity. Okay, gravity, that force that pulls us down, right? Okay. Shh. In the back, guys. Say it. Okay. Gravity is always pulling these supermassive stars toward their core, and fusion is pushing that gravity back, and you get this balance of forces. And this balance of forces allows stars just to be boring. But when that gravity starts to win because they run out of fusion, well, if you're running out of fuel for fusion, you can't fight the gravity starts to win. Okay, if gravity starts to win, the star will start to contract at the inner part. Michaela, what happens when stuff starts to contract and condense? What happens to the temperature?
It gets colder.
Colder? When
Hotter.
stuff gets hotter. There we go. When stuff is getting more pressurized and more contracted because it's running out of fuel and gravity's starting to win, the hydrogen, well, the hydrogen's been fused into what?
The
Okay, what's H plus H?
Hydrogen 3
Helium.
plus energy.
Helium. Good. Okay, you get helium. Helium. When a star starts to contract, it gets hotter at the core. As it gets hotter, it can start to burn helium. When it burns helium, it gets a lot more energy being pushed out because the reactions become much more intense. So it's pushing out more energy. So the outside of the star, even though it's the same amount of mass, swells up like a fat tick. Because we talk about the force of gravity pulling down and fusion pushing up. Now fusion's starting to win. So fusion's pushing that star really big and wide. For example, Earth is 93 million miles away from the Sun on average. Okay? Mars is another half that away from the Sun. The Sun will swell in our solar system. When it goes red giant, okay, our Sun will swell to this in 4 billion years. Don't worry about it. It's not going to happen tomorrow. When this happens, it will swell to the size of Mars's orbit.
That means we'll be involved.
Yeah. But don't worry. We have 4 billion years. You're not going to be alive. It's okay.
What about our children, friends?
Your grandchildren won't be alive. Don't worry. It's not going to be a problem. Okay. When the Sun swells to red giant phase, it gets cooler on the outside of the star. Now think about this. Think about this. Campfire. Got the ring around the campfire. It's a nice brisk day. We've all got our s'mores out and our hot dogs, and we're roasting stuff on the campfire. Okay. The closer you sit to the fire, the warmer it gets. The further away you get from the fire, the colder it gets. Well, think of, in the Sun, the campfire is the core. And the closer you get to the core, the hotter it gets. The further away you get, the cooler it gets. So if the Sun is going to expand like out to the orbit of Mars, even though it's really, really hot in the core, is it going to be as hot as it was before on the edges? No, right? Because it's so much farther away. So the color of the star is going to go from, if our star is yellow, it's going to go from yellow to, well, blue. What does blue mean with temperature? Hot. So it's not going to go blue, it's going to go the other way. It's going to go, if it's yellow, it's going to go red. Right? Remember Roy G. Biv? Red, orange, yellow, green, blue, indigo, violet. If our Sun is yellow, and these are cooler temperatures, these are hotter temperatures, if it expands, the shell will then, because it's further away from the fire, become cooler. Happy, did you get this?
You're talking about Mars, or?
Did you understand this?
Yeah,
Sort of, kind of?
Sort of, kind of, not really.
Well, let's start paying attention better. We'll get there.
I'll get it.
Okay. Do you guys ever notice, so you look up at the stars? I love the winter stars because the air tends to be a lot crisper, a lot cleaner, not as much pollution, not as much water, it's drier. You can see the stars better. So you look up at the stars and Orion shows up. Orion is the one constellation that, you know, it's got the 3 stars in the belt, one up here, a couple down here, foot here, foot here. Okay, Orion. This star in Orion is called Betelgeuse, or Betelgeuse. If you want, we're given a German name, Betelgeuse. We call it Betelgeuse. The top left, it is a red giant. If you look at the star in the sky, it is visibly red. The star looks red. Star down here, it's either this one or this one. I think it's this one. Could be wrong. Forgive me if I'm wrong. Is a blue star. It's very blue as compared to the red one. Not all stars have the same color. Just staring. Not last week when we had a really clear skies, I showed up in the morning, wow, boom, there it is right in front of me. You don't need a telescope, you need nothing. Sammy. Oh, you're not Sammy, I'm sorry, say it.
Where do you go to like look at them? Because I can never ever find them.
I was in the parking lot over there. Orion is always bright in the sky. Orion is a very bright constellation. Okay, and it's one of these giants. Okay. Do you guys have questions about giants in the giant phase?
I got a question.
What time did you see it at?
Red giants that are actually.
It's nighttime.
What was that?
It's not that from the red giants.
Depends on the size of the star.
Right, it was like.
So, if a star, like our star, will spend 90%, I don't have numbers off the top of my head. I can do math. So, if a star spends 90% of its life, listen, hush. If a star spends 90% of its life as main sequence, so if our star will live for 8 to 9 billion years, so you're looking at 8 billion years as a regular star, and then less than a billion as this.
So like a billion years ago. It's a long time, but not as long.
Yeah, but you have to, like a large massive star, its entire lifespan is about 14 million years. But 90% of that is as this. So as it gets to this stage, it starts to go faster and 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 faster. Boom. Okay, down here. Okay. Let me see how we do for time. Okay, Sean.
Alright, so I saw this, right? I thought it was like a moon. One of those things.
How would you?
You've never seen this.
Wait, no.
Without a really, really super fancy, awesome telescope, you've never seen this.
Alright, the moon was orange, alright?
When the moon is orange, it's just low in the sky, and we're looking through more atmosphere, and the filters of light through the atmosphere, as light filters through, makes the moon look orange and huge in the sky. It's often called a harvest moon. It's really beautiful when you see it like that. But it's not one of these.
So it's not that big. It's just the atmosphere.
It's just the atmosphere magnifying and making it look big.
What about when like sky is like pink? Like different colors.
Same concept. The sun is filtering through all the atmospheres and pollution and dust and stuff in the sky, and then we get those really, really pretty sunsets. But that's just the filter of our atmosphere. Okay. Now let's see. I need to talk about this again briefly. I don't want to spend too much time here. Hydrogen plus hydrogen is helium. Okay, 1 plus 1 is 2. I don't have my periodic table of the elements in front of me, but eventually this process that caused the helium will run out a lot faster than hydrogen. Does that make sense? Because if all the 1s have to make 2s, it's going to take a long time. But now all the 2s are making 4s, and all the 4s are making 8s, and all the 8s are making 16s. You see how this works? And it's just going to go faster and faster and faster and faster and faster. The star gets really unstable, gets really swollen. Well, eventually this will fuse all the elements in the periodic table up to what element? Gold. What was the one, that nuclear turnip? Iron. Okay, it fuses this until it gets to Fe, is iron. Now when iron is being fused, okay, that reaction that creates the iron does not create either as much energy or actually absorbs some energy. So now the balances are out of balance again, because fusion has been winning and winning against the gravity that's pulling down. Okay. Gravity's pulling down, fusion's pushing up from the core. But now when we get to iron, it's fusing iron and making more and more iron, well, it's less and less energy, gravity starts to win, and before you know it, boom, we hit that point where the star starts to collapse and die. Okay, when the star starts to collapse and die, if you're at a red supergiant, it's because it got to iron. If you're at a regular giant, it's gotten somewhere about carbon or somewhere else. These things don't explode. These things just swell and then shrink. These things, woo, they get exciting. Okay, well, let's talk about the swell and shrink really quick. Okay, now we are in a new category. Okay, you see we're in the next category? In your notes? Writing notes? Okay. If this swelled to the size of Mars, and now it shrank all the way down almost to the sun's core, what's left is this little dot in the middle. What is this little dot? A white dwarf. But it leaves a lot of the gases and the dust of the outer rim of the star behind as it shrinks, because it shrinks really fast. Leaves a lot of those gases behind, and it leaves a cloud of gas and dust. What is a cloud of gas and dust?
Nebula.
A nebula. Why they call it a planetary nebula? It's the most confusing thing in the world to me. I mean, why don't we call it a red giant nebula? That would make a lot more sense, but they call it a planetary nebula. Just know that a planetary nebula is the remnants of a red giant. Okay? This is where our sun will go. Our sun will do this and go back to this stage. Eventually, the light will go out of the white dwarf and it will just disappear in the sky. Physics. Physics models.
So the stars we see are
Some of them are white dwarfs, some of them are, but most of the stars we see are average stars, or normal stars, main sequence stars. Okay, so that's the story for our sun. What's going to happen to our sun? Tatiana, what's going to happen to our sun?
It's gonna get bigger.
And-
Bigger.
And then what's going to happen to it?
It's collapse.
When it collapses, what will happen to it?
It'll spin. Or no. Or no.
You're getting your terms confused. It's going to collapse into a white dwarf and leave a nebula around it. Okay?
When that happens, what will happen to Earth?
Earth will have already been destroyed when it swells to red giant.
Wow.
Why? Oh, it'll be engulfed in.
Because it'll be engulfed by the sun. Good. Okay. Now when we deal with, here's the fun one. I've been waiting all year for this. Okay. The giant star, the super giant star, has gotten to iron. It is now full of all of these different elements and shells of elements. It's actually doing fusion in different levels, like a gobstopper. You know, like gobstoppers are like small layer, then another piece of candy, another piece of candy.
Yeah. I hate those.
You've never had an everlasting gobstopper?
No, I haven't.
Those are from the 1980s.
Yeah, it's the same concept.
I've only
Wonka.
Okay. You'll like the inside of the star will look like this. At the bottom you'll have iron. And then you'll have another element. Another element. Another element. And the core will have this shell layer to it. Well, when this happens, let me draw this bigger. My beautiful sun here. Okay, gravity is pulling in this direction, fusion is pushing in this direction, the forces are balanced to a point. But when iron gets in the scene, the forces run out of juice. There is no more fuel. The star loses the battle to gravity, and who wins?
Gravity.
Who always wins?
Gravity.
Gravity. Now, we've reached iron. Gravity causes the entire star to catastrophically collapse, like that. Okay? It starts to zoom toward the center.
It sounds like there's a jet somewhere.
It's not great.
It's probably a storm, guys. We're under a tornado watch. It's okay. Stop. If there is, okay, if you can't listen, if there is a tornado warning, we do what's similar to a fire drill. We go downstairs, and instead of going outside, we sit on the wall of the hallway right below us in cosmetology, and you bend down, and everybody's okay, and we wait till the storm passes. Okay, moving on. Quit giving me this backhand. Okay, when this catastrophically collapses, everything starts to shoot. Like as fast as gravity can pull it down, the outer rim of this red supergiant zooms toward the center of the star. It will do one of two things. It will do A, neutron star. It will go supernova. Well, all of that outer stuff hits the core and either will act like a trampoline and bounce off the core. If that happens, you get a giant supernova explosion that's brighter than any galaxy out there, and that's where it starts fusing everything above iron, like gold and all this other stuff. Mercury and all the heavy elements get fused in that explosion, and then you're left with this nebula, this remnant of the star that exploded, and at the center you'll have a neutron star, an extremely fast spinning little star that's emitting immense amounts of gamma radiation. Yeah,
We'd be able to see supernova and not and stuff.
absolutely, it would be bright.
Fire and stuff.
Yeah, this is the Crab Nebula. I think it's the Crab Nebula. This is the remnant of a supernova we saw in the 1800s. This is the one. They saw it bright in the sky. It's crazy. I wish I could see one. That'd be awesome. So here we have the neutron star that's left. Now the other option, and this is where it really gets kind of fascinatingly, mysteriously crazy. If the star is big enough, it will not bounce off the core. The core will completely collapse. Gravity ultimately wins and sucks the star down into nothingness. Okay? Mathematically, black holes cannot exist. But they do exist, and we see them. So, what you're seeing here is this accretion disk of stuff spinning around the black hole, and you see these jets. The stuff enters the black hole, it throws off these real huge jets of energy. Okay. So a black hole is a star that is so gravitationally powerful that light cannot escape the star. To escape Earth, you have to go like as fast as a bullet out of a gun to get out of the Earth's atmosphere. Like you're going like 2,000–3,000 feet per second. Okay, not too bad. To escape from a black hole, you have to be going greater than 186,000 kilometers per second. I'm not sure what the speed of light is in miles. It's like 300, whatever it is. I don't remember. It's very fast. Okay, so that's a black hole. Those are really cool. All right, do you guys have any questions on this chart? We have. As best as you can. You don't see the black hole, you see the black hole effects on everything else around it. Which is kind of why they're cool.